In this video, we're going to explore limiting reactants. In most chemical reactions, there will be an insufficient amount of one of the reactants in order to consume the other completely. In other words, one of the reactants will limit how much product we're able to make. And so the theoretical yield of a reaction is limited by this limiting reactant. Let's look at a simple example. Let's say we have 32 nuts and 28 bolts. One set consists of one nut and one bolt. And so we can set up what looks like a chemical reaction to explore that relationship. One nut and one bolt gives us one nut-bolt set. And so if we want to know how many sets of nuts and bolts we can only make 28 sets because we only have 28 bolts. Therefore, the bolts are our limiting factor in this reaction. Let's say we have a different nut-bolt setup in which we need 2 nuts for every 1 bolt that we have. And so our reaction changes. We now have a coefficient for the number of nuts. 2 nuts plus 1 bolt gives us our nut-bolt set. And so in this case, it will be the nuts that are limiting, because we can only make 16 sets total, since we have 32 nuts, but need 2 per set. And so the number of nuts that we have limits the nut-bolt sets that we can make. In this example, we're going to look at how many tricycles we can make. Let's say, for instance, we have 27 wheels and 12 handlebars, and so we want to know how many trikes we'll be able to make from that. Let's set this up like it's a stoichiometric problem. And so we know that we're starting with 27 wheels, and we want to know how many trikes we're going to be able to make from that. And so our conversion factor would be that we can make 1 trike from 3 wheels, and so we can make a total of 9 trikes. And then from our 12 handlebars, and our conversion factor of 1 trike per 1 set of handlebars tells us that we can make 12 trikes from those 12 handlebars. And so therefore, in this case, we can see that the wheels would be our limiting factor, because we only have enough wheels in order to make 9 trikes. And the handlebars we would consider to be in excess. And so let's take a look at a chemical example. In this example, we're going to react together aluminum and oxygen, and we want to know what the limiting reactant is if we start with 50.0 grams of both of those reactants. And so our ultimate goal is to calculate the theoretical yield for that reaction. And our first step, as in many stoichiometric problems, is to put together our balanced chemical equation, which we have here. 4 moles of aluminum plus 3 moles of O2 will give us 2 moles of aluminum oxide. What we want to do then is convert both of our starting amounts from grams over to moles. And so, as we've been doing all along, we're going to use our molar mass of each of the reactants in order to do that. 50 grams of aluminum divided by our molar mass gives us 1.85 moles of aluminum to start. And 50 grams of O2 divided by its molar mass gives us 1.56 moles of O2 to start. Next, we want to compare our starting moles of aluminum to our starting moles of O2. So we calculated before that we had 1.85 moles of aluminum and 1.56 moles of O2. So we divide those by each other, and we see that what we have to start with is 1.19 moles of aluminum per every 1 mole of O2. Now we want to compare that to what's required in our chemical reaction. From our balanced equation, we see that we need 4 moles of aluminum to every 3 moles of O2, or in other words, we need 1.33 moles of aluminum for every 1 mole of O2. However, we see that we're actually starting with 1.19 moles of aluminum to every 1 mole of O2. And so that means, since the 1.19 that we have is less than the 1.33 required, aluminum is going to be our limiting reactant in this reaction. And so what we can do from there is we know that we're going to have 1.85 moles of aluminum to start. And so then we simply calculate the rest of the reaction through based on that starting amount of aluminum. So we have our stoichiometric ratio of aluminum oxide to aluminum, and then our molar mass of aluminum oxide, for a final amount formed of aluminum oxide of 94.3 grams. So that's one approach in which we simply compare the moles of each reactant that we have to start. Another approach is to simply do out the entire calculation based on both amounts of starting material. And so first, set up a stoichiometric problem, starting with our 50 grams of aluminum. And as we've done before, we first convert that to moles of aluminum. We use our stoichiometric ratio to go to moles of aluminum oxide, our molar mass of aluminum oxide, to see that 50 grams of aluminum will form 94.3 grams of aluminum oxide. We then go through the entire calculation, but using our 50.0 grams of O2 as our starting material. Convert that over to moles of O2 using our molar mass. Use our stoichiometric ratio to convert to moles of aluminum oxide. Our molar mass of aluminum oxide to convert then to grams of aluminum oxide, which shows us that 50 grams of O2 will produce 106 grams of Al2O3. However, we saw in this reaction that our 50 grams of aluminum only produces 94.3. And so that is the most aluminum oxide that can be made, because that's how much our amount of aluminum will give us. And so since aluminum as a reactant forms less aluminum oxide than oxygen, that means that aluminum is our limiting reactant and will form 94.3 grams of our aluminum oxide. And then if we wanted to go one step further and calculate a percent yield based on an actual amount of aluminum oxide formed, we can set up our percent yield equation of our actual amount. In this case, our experiment yielded 48.5 grams, divided by the theoretical yield we just calculated, multiply by 100 to convert to a percent, for a 51.4% yield for this reaction. Let's go through another example. In this example, we're going to react 10.0 grams of gold and 10.0 grams of chlorine and heat those up until our reaction is complete. We know that our product is gold-3 chloride, and so we want to know what reactant is our limiting reactant, what is the mass of gold-3 chloride actually formed, and we also want to know what mass of the excess reactant remains behind after the reaction is done. Our first step is going to be to write out our balanced chemical equation. We have gold reacting together with chlorine, which recall is a diatomic, in order to form gold-3 chloride. And then in order to balance this equation, we can see that we have an odd number of chlorines in our product side and an even number in our reactant side. And so the first thing that we see we have to do is probably double our number of gold chloride molecules in order to get an even number of chlorines. And so from there we see that we're going to need 2 golds and 3 chlorine molecules to react. And so we now have a balanced chemical equation. Our next step is to convert our given grams of both reactants into moles. So we start with 10.0 grams of gold. We convert that over to moles using our molar mass. And then we do the same for chlorine. And now we want to go ahead and divide those amounts by each other. Which gives us a ratio of starting with 0.360 moles of gold per every 1 mole of Cl2. And now we want to compare that with what's given in our balanced chemical equation. We see in our balanced equation we need 2 moles of gold per every 3 moles of Cl2. And so that reduces down to needing 0.667 moles of Au per every 1 mole of Cl2. And so again, let's keep in mind that 0.667 moles of gold is how many are needed per 1 mole of Cl2 from our balanced equation. But we're only starting with 0.360 moles of gold for every 1 mole of Cl2. And so what this tells us is that in this equation, gold is our limiting reagent. And so our next step then is to find what is the actual mass of gold chloride that is formed. We calculated that we're starting with 0.508 moles of gold. And so then we just set up the rest of our stoichiometric calculation to find our mass of gold 3 chloride. We see from our balanced equation that for every 2 moles of gold 3 chloride formed, we start with 2 moles of gold, and then we use our molar mass of gold 3 chloride to convert to grams. For a calculated theoretical mass of gold 3 chloride of 15.4 grams. Lastly, we want to calculate how much of our excess reactant remains in our reaction. We found that gold is our limiting reagent in this reaction. Therefore, chlorine is our excess reagent, and some of that is going to remain behind. In order to find out just how much, we're going to have to backtrack. We're going to use the amount of gold 3 chloride that was formed to calculate how much chlorine was actually used in the reaction. We can then subtract that from the amount of chlorine that we started with to find out how much we have left. And so we calculated in the last slide that we would form 15.4 grams of our gold chloride. So we set up a stoichiometric problem to find out how much chlorine was used. And so, like in all stoichiometric problems, our first step is to convert to moles of the gold 3 chloride using our molar mass. And then use our stoichiometric ratios to convert to moles of chlorine. And then finally, our molar mass of chlorine to calculate how much chlorine was actually used. And we get 5.40 grams. So remember, that's the amount of chlorine that was used in our chemical reaction. We know that we started with 10.0 grams of chlorine, so we can subtract the 5.04 grams that were actually used, and we find that we are left with 4.60 grams of chlorine in excess. And so that's how much chlorine will be left over in our reaction. Let's work our way through a couple more examples. In this example, we're going to look at our reaction between silicon dioxide and carbon to form silicon carbide and carbon monoxide. We want to know if we start with 5.00 times 10 to the third grams of each reactant, how much silicon carbide will theoretically form. Let's work through this example by fully calculating through the theoretical yield of silicon carbide based separately upon both reactants. And so first, we're going to start with our 5.00 times 10 to the third grams of silicon dioxide. And we find that based upon that amount of starting silicon dioxide, we are theoretically going to form 3.34 times 10 to the third grams of silicon carbide. Next, we're going to work through the entire calculation and find our theoretical yield of silicon carbide based upon our starting amount of carbon. And in doing so, we find that that amount of starting carbon will theoretically produce 8.35 times 10 to the third grams of our silicon carbide. And so we can easily see that the amount of silicon carbide formed from our silicon dioxide at 3.34 times 10 to the third is significantly less than the amount of silicon carbide that can be formed based on the amount of carbon. Therefore, the most amount of silicon carbide that can be formed in this reaction is our 3.34 times 10 to the third grams of silicon carbide, and that silicon dioxide is our limiting reactant. Let's look at a final example. Here, we're going to look at the reaction that forms the chemical known as DDT. DDT is an insecticide which was banned by the US government long ago because of the hazard that it poses to fish and birds. We can look at its preparation though, and we see the chemical formula as follows below. And so we want to know if 451 grams of chlorobenzene reacts with 368 grams of chloral, and from that reaction, we actually yield 507 grams of DDT. We want to know which species is the limiting reactant, and then we also want to be able to calculate our theoretical and percentage yields. And so we're going to approach this problem in even a slightly different way than the others we have looked at. Here, what we're going to do is run the calculation through and find how many moles of DDT that can be produced based upon our starting amounts of our reactants. And so, in order to find the amount of DDT that can be formed from chlorobenzene, we set up our stoichiometric problem, and we see that starting from 451 grams of chlorobenzene, we are going to form 2.00 moles of DDT. Next, we want to look at how many moles of DDT might form from our 368 grams of chloral. And we see that based upon that starting amount of chloral, we would be able to form 2.49 moles of DDT. Therefore, since our amount of chlorobenzene forms a lesser amount, chlorobenzene is our limiting reagent, and we would be able to form 2.00 moles of DDT given these amounts of starting material. And so then, we can just finish off the calculation. We know that we're going to form 2.00 moles of DDT, and we can simply use the molar mass of DDT to then convert that over to grams. For a final theoretical yield of DDT of 709 grams. The last thing we want is to calculate our percent yield. Theoretically, we calculated that we can make 709 grams of DDT. However, this particular reaction only yielded 507 grams. And so in order to calculate our percent yield, we're going to take our actual amount of the 507 grams, divide that by our theoretical yield of 709 grams, multiply by 100, for a percent yield of 71.5%. One last example. Here we want to know what the percentage yield is of ammonia if 50 grams of nitrogen and 50 grams of hydrogen react to form 30 grams of ammonia. And so our first step is going to be to set up our balanced chemical equation. We know that both nitrogen and hydrogen are diatomics, and so N2 plus H2 react to give us NH3. And then in order to balance this equation, we see that we have 2 nitrogens on our reactant side. So we need a 2 in front of our NH3, giving us 6 hydrogens total. And so we now need a 3 in front of our H2. And so, in order to find our percent yield, we have to first calculate our theoretical yield, which means finding out which of these is our limiting reactant. And so, what I would do here is set something up any way that we've talked about so far. You can either compare your mole ratios in the beginning, work it out through to moles for each and find the limiting factor, or calculate the whole thing through and find out which forms less. Any one of these processes will work. What I'm going to do is calculate it the whole way through based upon both. And so first I'm going to start with my 50 grams of N2, and I'm going to set up my stoichiometric problem, and I find that starting with 50.0 grams of N2 will theoretically yield 60.7 grams of NH3. Next, I'm going to do the same thing, but based upon my 50.0 grams of H2. And I find that based upon 50.0 grams of H2, I can form 281 grams of NH3. And so I know that the N2 is my limiting reactant because it forms the least amount, and that my total theoretical yield of NH3 is going to be 60.07 grams. Finally, I want to calculate my percent yield. I actually formed in this reaction 30 grams compared to a theoretical yield of 60.7 grams, and multiply by 100 for a final percent yield in this reaction of 49.4%. And so in this video, we've explored the idea of limiting reactants. We've looked at the fact that in most reactions, one of the reactants will limit how much product is able to be made. And we've looked at several different ways in order to determine what the limiting reactant is and how to calculate our theoretical yield based upon that. Any one of those methods would work. Find whichever one works out best for you and go from there. I hope this video has been helpful. For more help, please be sure to visit the website.